Good day and welcome to CP419 class. Recall that in our previous lecture, we have learned how to design combinational logic circuit from given set of conditions. Today, we will learn about combinational logic functions. In computers, in other digital systems, there are some special functions in which they are combinational in nature. By this, we mean that they are designed from combinational circuits in which their outputs only depend on the current input and not on the previous or past input. Today, we will look at into the description of some of those combinational logic functions, as well as we'll look at into their the logic diagram, as well as we will be able to look into some of the functions like the half adder, the full adder, decoder, encoder, and comparator. Now, I will start with the half adder. So what is an half adder? An half adder is actually it's a function which perform a sum operation of 2 bits. It takes 2 input bits and it sums the bit, producing the sum output and the carry out output. The sum output is defined by the exclusive OR function of the 2 input bits A and B, while the carry out is defined as by the AND operation between the inputs A and B. Here is the truth table of half adder. You can see that the C out is the AND operation between A and B, in which you see that there is only I C out when both A and B are also I, or when both A and B they are 1, C out is 1, which describes an AND operation. Whereas the sum, it's actually it's the exclusive OR function or operation between the 2 input bits. Another combinational logic function that we will look into is the full adder. The full adder, similar to half adder, is also able to perform addition of 2 input bits, but with an additional input line which takes the input carry. So it adds 2 input bits with an input carry, and it produces 2 output bit and output carry. The output bit is the sum and the output carry. The sum function is defined by exclusive OR operation between A, B, and C in gives us the sum function, whereas the C out is defined by AB plus A exclusive OR B and C in. Here is the C out. We can question what is the function of this carry in and carry out. The carry bits, it's actually it can be from it can be used to link. It's an internal function which is used for internal calculation. It's an internal bit which can be used for internal calculation when you connect 2 or more full adders together. I will describe that shortly later. Here is a full adder truth table. You see here the C out, which describes the and C out, rather, it describes A and B, or A exclusive B and C in A with the C out. Whereas the sum, it's defined by an exclusive OR function. Here is the circuit diagram of full adder. We see here that this line, it's just represents the logic diagram, and we have already defined that the sum is defined by exclusive OR operation. And here you see A exclusive OR B. These are two. It is one exclusive OR gate, which again combines with Cin to give the sum output. And for the other line, it defines this operation is the gate that is able to carry out this operation. And both lines are connected to the same in parallel. They are connected in parallel to the input A, B, and C in. The full adder can also be represented by a certain logic symbol. Here is a logic symbol of the full adder, which here this line, it shows the inputs A and B, and C in is carry in. A carry in it's actually takes in bits from other operations. It takes in bits from input bit from other operation. And C out, it's the extended bit of the sum will be carried out will be taken to the carried out. We can form full adder by combining two half adder as shown here. Here we see that it's able to describe. We connect the two half adder together to give us full adder. Now, recall that I mentioned before that the usefulness or the importance of the carry bit. For example, it's to be able to connect one adder to the other. So we take in the carry in of this and connect to the carry out of the next full adder. And this is done when we want to combine two or more full adder in what we call parallel binary adders. And parallel binary adders, they are required to extend the number of bits that can be added. Recall that full adder can only add two single digits and a carry. Two single digits and a carry. In order to add more bits, we can combine two full adder. We can to add more bits. So, for example, here in this case, we want to add two bits, A1, B1, and A2, B2. We want to add it together. And we see here that we required two full adder, and the C in of this second full adder is connected to the C out of the first full adder. Here is the least significant bit, and here is the most significant bit. Also, to add 3 bits, we need 3 full adders, as shown here. To add 3 bits, we need 3 full adders, and so on. If you need to add n bits, so we need n full adders to be able to add n bits. Shown here is a cascade of 4 full adders, which which is used to add two 4-bit numbers. Here we see A4, A3, A2, A1, B4, B3, B2, B1. These are the 2-bit. These are the 4-bit numbers. So we can use this parallel 4-bit parallel adders to add them. Now, what about the truth table for each stage of 4-bit parallel adder is described here. We have the carry of the previous. This is a carry Cn-1. Then we have An, Bn. They are the inputs. So the carry of the previous, that is Cn-1. So and then we can use this truth table to, in fact, perform addition. We can use this truth table to perform addition, as we see shortly in this example. Now, he said use the 4-bit parallel adder truth table to find the sum and carry for the addition of the following 2-bit numbers if the Cn-1 is 0. So, for example, we want to add 1100 and 1100 here. Now, we assume that Cn-1 is 0. Now, if you take the least significant bits A1 and B1, so what are the inputs? The input there is 0, 0. A1 is 0, that is for n equals 1. A1 is 0 and B1 is also 0. And we now require also Cn-1. Cn-1, here we were told that the previous carry has been 0. Now, if we take this information and look at the table here, you see that when Cn-1 is 0 and A is 0 and B is 0, it corresponds to this first row. And what is the sum and carry in this case? Sum is 0 and carry is also 0. And that is why we have summation 1 equals to 0 and C1 equals to 0. Now, for n equals to 2, we take what is now Cn-1, the previous carry. We take that one first, which is C1, so which is 0, right? And if you now take n equals to 2, we take the second bit here, so which is A2 and B2. So what is A2? A2 is 0, B2 is also 0. So A2 equals 0, B2 is 0. What is now Cn-1? That is this one here, which is equals to 0. So this also corresponds to first row of the table, and in which the sum is 0 and the carry is 0. Again, for n equals to 3, so we take the carry. This carry here is this one here, and which is also 0. And for n equals to 3 is A3. So what are the bits? Is 1 and 1 with a carry of 0. And let's look at the table again, 1 and 1 with its carry of 0. So this is 0, 1, and 1. It corresponds here to the fourth row. And in this case, what is the sum? The sum is 0 and the carry is 1. So here the sum here is 0. That's why the sum is 0 and the carry is 1. Now we take this carry and we put it here in the fourth bit. That will be the carry for the fourth bit. That is 1. So what is now the fourth bit here? So A4 is 1 and B4 is also 1 here. So we have 1, 1, and 1. So if you look at here again, so we have 1, 1, and if the carry is 1, so it corresponds to the last row, which is in which the sum is 1 and the carry is 1. So now we have been able to use, so we have determined summation 1, C1, summation 2, C2, sum 3, C3, sum 4, C4. So what will now be the C4 becomes the output carry, which is 1. So what the sum of these two numbers, 11, 1100 and 110, is now we take the carry first, we write it down, we put this carry, and then we now start from the bit 4. So that will be 11000. 11000. That is the sum of these two numbers using the adder. Now, I want to quickly say that we can also cascade two 4-bit adders to form an 8-bit adder. Now, if you are going to think a little bit, what is actually an physical application of an adder? We can use an adder to implement a simple circuit, a simple counting circuit. For example, here I shown here that actually I will have mine to for this for a project application. We can actually use it to design an electronic voting system for Nigeria's National Assembly. We can use full adders. We can implement 120 position of adder system. Now, let me show you how that can be done. Let me share another screen. Okay, shown here, it's actually a 6-position adder module in which we can use this system to take count of 6 position. For example, if you want to take electronic voting counting of yes or no, here we have the upper part is a yes logic, so it's those who will choose yes, whereas the lower part is a no logic. And we can see this line is connected to yes, and this is to yes. So everyone that chooses yes is going to count and sum it up and show it here in this 7-segment display. And everyone that chooses no, it will count it, sum it up, and show and display it. Display it here on this 7-segment display. So this is actually a simple voting system which can be used which can be implemented using a full adders. We can scale it up actually to any number of position that we want, maybe 120 or etc. can be scaled up. And how can this be actually done in real time? So we can actually implement this on a programmable logic device. So we can describe this circuit by a Verilog code and put it on a programmable logic device, and then it can then implement this circuit that we want to do. And in fact, we also have some special ICs that can also perform some of these digital operations. So, for example, like the adder, we have an IC that can perform adder and so on, but it can also be implemented on a programmable logic device by using by writing the description but with an hardware description language and downloading it on the POkkAquD device. We will still describe that one in detail later on. So let me continue and share the other screen. One moment. Okay, so we will continue with another combinational logic function, which is a comparator. A comparator, basically what it does is to compare magnitude of two binary digits. So it compares magnitude of two binary digits. In the simplest form, a comparator circuit, it determines whether two numbers are equal. That is what it does. It determines whether two numbers are equal. It can also determine whether one number is greater or less. It can as well do that. Now, let's look at a simple comparator. The simplest comparator that we can have is actually an exclusive OR gate. An exclusive OR gate is a comparator which check whether two bits are equal. An exclusive NOR, rather. It's a comparator, can be a comparator which check whether two bits are equal. Look at this. When we have 0, 0, the output will be 1. So it says that the two bits input, they are equal. But when we have 0, 1, the output will be 0. Or when we have 1, 0, the output will be 0, which shows that they are not equal. Also, when we have 1, 1, the output bit the input bit, they are equal. So this is a basic comparator operation which checks for equality of 1-bit numbers. Also, it is possible to have equality comparator for 2-bit numbers shown here by using we use two exclusive NOR gates, and actually what is done here is to compare each of the bits by itself. For example, the two bits, they are A0 A1 and B0 B1. So these are the two bits. These are the two bits numbers. Then the first exclusive NOR, it checks whether the least significant bits of both numbers, they are equal. And if it is 1, if it's higher, and if it's also higher, it's now combined by an AND gate. It will give high, showing that both bits are equal. That is when A equals to B. That means A is just exactly the same as B. Now, we could also have a comparator module with an inequality sign. For example, here it's a 4-bit. This is a comparator that can compare a 4-bit number, and it has 3 outputs, which can indicate whether the A is greater than B, or A equals to B, or A less than B. It can give 3 outputs. And in fact, it checks the bit line by line. For example, if B3 is 1 and if A3 is 1 and B3 is 0, it shows us that A is greater than number B. But if A3 is 0 and B3 is 1, it shows that A is less than B. But if if A3 and B3, if they are equal, then it moves to the next bit. That is how it compares. Decoder. Decoder is a digital circuit that detects the presence of a specified combination of bits or code on its input, and it indicates the presence of that code by a specified output level. So what decoder does is that it checks at the input whether we have some combination of bits, and then it now translates that combination of bits into a specified output level. That is what a decoder does. And in general, a decoder, it has n input lines to handle n bits, and it forms 1 to 2 to power n output lines to indicate the presence of one or more n-bit combination. Now, this is a basic decoder. This basic decoder here, it can be used for decoding logic of a binary code. Here it shows it decodes this binary code 1001, and with an active high output, which means that the output has to be 1 is a logic circuit that produces high output when the input is actually 1001, and we can design that, and we can also we can make it to be active low. That is, we can determine the logic that required to decode a binary number producing a high level on the output. It is also possible to make to detect the binary code to produce an active low output. It's also possible. We have another decoder, which is a BCD to decimal decoder. So a BCD to decimal decoder, it converts from BCD to decimal. This example is the 8421 code, which converts the 8421 code into a decimal, 8421 BCD into decimal. Here is the BCD to decimal decoder function. This is the decimal digit, and these are the BCD codes. And this is a typical IC that can perform BCD to decimal decoder. In fact, many of these functions, they can be represented by an integrated circuit. Let me show here. Let me show here. Right. This is an IC, which it is 74LS83. It's actually a 4-bit full adder IC. So this IC can perform full adder operation. And you can see from the pin configuration that A1, A2, A3, A4, they are the input of the adder circuit for, and B1, B2, B3, B4, they are the. So now, how many? It's actually 4-bit full adder. So that means it can add two 4-bit numbers. And here is a CO, the carry out, and this is a sum, S1, S2, S3, this is a sum. And this is the carry. These are the pin numbers, and this is the pin name. So to show you that some of these combination circuit, we have some specialized IC that can do the operation. Here is another one. This is a 4-bit full adder. I think is the same as we also have comparator. We have comparator too, which can perform comparator operation, and IC that can perform comparator operation. So in addition, we can also implement this function on programmable logic device, like I said before. So you can either buy a fixed IC or you implement the function on a programmable logic device. One moment. Yeah. So encoders, let's move to encoders. Encoders, they are an encoder, it accepts an active level on one of its inputs representing a digit such as decimal or octal, and convert it to a coded output such as BCD. So encoder is just the reverse of decoding. Decoding it checks some bit combination and convert it to a certain level of output, whereas encoding, it takes an active level of input and convert it to a certain bits combination. For example, you can have an encoder that can convert a decimal to a BCD. Encoders can also be devised to encode various symbols. For example, we have encoders that can encode alphanumeric and numeric characters. The process of converting from familiar symbols or numbers to a coded format, that is called encoding. Here shown here is a BCD to is a decimal to BCD encoder. It can convert from decimal digit to BCD code. And there are several other combinational logic functions which I will refer you to the reading text to look into the code converter, multiplexers, the multiplexers, the parity, generators, and checkers. All these are other combinational logic functions which, for example, code converter, as the name implies, can perform conversions from one code to another. Multiplexer, it can combine two or more binary lines together into a single line. The multiplier can separate a combined channels it can separate combine into separate lines. And also we have parity generators and checkers, which is used to usually for error detection and correction. So thank you for your attention.